Okay, welcome to the next session. So this time we'll be talking about something called hidden Markov model. So let me make sure that we are being recorded. And so, okay, we'll talk about hidden Markov model. Now, they are kind of an application of what we did earlier. So, so we want to talk about, it's like last time we talked about Bayes network, and Bayes network are a series of nodes connected to each other like this. Maybe this is connected, maybe this is connected like this, maybe there is other connections or network. And we have also checked how dependencies flow on a network. So we have a base network, one of them influences the other depending on where the arrow is going. And in fact it is both ways. And we also tracked how to figure out dependency tracking. We also learned to do this on the network. So which node influences the other node? How do they influence each other? That is what we talked about. Now, a classic application of that is called hidden Markov model. So hidden Markov model is a Bayes net, but it is a special type of Bayes net. It is a Bayes net where the word hidden is important because there is a node that is hidden from public view, and the hidden causes something to happen. It causes a node to, it influences a node. This is hidden, this portion is hidden, and this portion is visible. Now the hidden node, which is this one, influences the observed node right here. And it also influences one more thing. It influences the next node. So you can think about it as a sequential data. So this may be at time t equal to 1, this may be t equal to 2. And every time step, there is a hidden state and there is an observed state. And the game goes on until you decide to stop. So that is the game. Name of the game is Hidden Markov. So this plays a very important role. Why? Because it influences two things. It influences the uh, observation. So you could say, hidden one. So this could be hidden state one. This could be observed state one. Some people say, one, or they say y1 also. So y1 is the hidden state, x1 is the observed state. Now, this is hidden. We don't know anything about this. So, and what type of node is this? It is a diverging node because two arrows going out. Diverging node, we do not know anything. So what does that mean? It means that these two nodes influence each other. I hope you got this idea because I have diverging node. A diverging node is this. And if you know something about this node, then it would block. If you do not know anything, it would allow the dependency to flow. So I do not know anything about the hidden node, which means these two may influence each other, this one and this one. Okay, anyway, but the game keeps on going like this and this. So you can ask, well, what do we want to do with that? We want to be able to do several things. One is we want to look at this and then we want to predict the hidden state. So you could say, okay, I know the outcome at x1. What is the hidden state at time 1? Then I could say, okay, what is the hidden state and what state does that lead to? So several questions you can answer, like y1, what is one? You are observing x1. So you can say x1 is the observable, what could be y1? And then y1, what could be y2? Similarly, you can observe x2. So you have observed x2, but similarly you can try to predict what is y2 and then the game. You could also say, I know x2, I have a guess about y2. So can I say what is x3? Maybe you could be asked such a question. So this is a classic example. Now I want to tell you this thing that data is sequential. What do I mean by that? Is data is um, ordered. So this is occurring at time 1 or place 1. This is place 2, place 3. So we have this sort of a network. Now, what could be the application of this? For example, a robot is watching a human. So the human has two states at every time. So this is time equal to 1. What is the state? Well, there is a hidden state, um, this, and there is an observed state. So hidden, observed. Now, hidden and observed state are there. So I know that the hidden state is one of two values. Now in this case, they have said y is the observation, x is the hidden state value. It doesn't matter, there is a convention x. So x can belong to only two things, as x can belong to either h or s. So the inner state of the person could be happy or sad, and the observed state of the person could belong to four categories, which is watching the Game of Thrones, sleeping, crying, or Facebooking. Four possible values of Y, observed state. So the robot is observing a person at time t equal to 1 maybe. He observed a person into one of these states. Then time t equal to 2, game goes on. So um, observable is one of these. So maybe t equal to 1 is the first hour. The first hour the person might be sleeping. The second hour the person might be Facebooking. The third hour it may be this. Fourth hour this. So this is the observed state. So observed state, another way to say that is you always know this. There is no ambiguity about it. And then unknown state or hidden state, which is this and this, you do not know that. There is no doubt about it. Do not know this, the hidden state. So you have to understand these terminologies before we proceed further. And so one of the examples could be the robot is watching the person. So this is observable, like I always say, this is observable and this is hidden. So I don't know what is the hidden state at t equal to 1. But I do observe the person W watching the Game of Thrones. Then it leads me to time 2. I do not know the hidden state of the person. It may be happy or sad. But I do observe the person sleeping, time t equal to 2. T equal to 3, I don't know what jump he made. Maybe he went from a happy state to sad state. He might have a bad dream or something. And in the third time, t equal to 3, the person starts to cry. Observable. I do not know the state. It's like, this one. Um, I'm going to say I don't know the state. And then the last time, this is t equal to 4, the person starts Facebooking. Now I can ask you, what is the likely state at each point, or likely hidden state at each point? So, I mean, there'll be some technique to figure that out. Now, that is great. We have this observable. What data are we given in a hidden Markov model? Well, what data does the robot have? It has the prior probability. Prior means at time t equal to 1. It's like when you start the game, there is 80% chance that the person is in a happy state, 20% chance he is in a sad state. So when you start the game, which is this is the game starting, and when you start the game, the priors is sad 20%, happy 80%. So based on that, you will, choose the state. It's like, you are going to flip a coin. The coin has not 50-50. It has like, two sides, side one, and on the other side is side two. And the probability of landing on side one maybe 80% and side two maybe 20%. And you flip this coin and you see what you get maybe. Then there is something else, which is the emission probability. What is emission probability? Is suppose you are in a sad state, this, then how likely are you to be doing something? That is called emission probability. So if you are in a sad state, what is the probability that you will be watching the Game of Thrones? 10%. This one. What is the, if you are in a sad state, what is the probability that the observed state may be sleeping? Sad sleeping maybe 30%. Sad and crying maybe 50%. What is left? 8, 9 is 10% of whatever is left, Facebooking. Similarly, if you are in a happy state, there is a 30% chance watching the Game of Thrones, 40% chance you are sleeping, 10% chance you are crying, maybe it's a happy crying, and 20% chance you are Facebooking. All of this has to add up to 1.0 because given the person is in this state, hidden state, he has to be doing one of the four physical things. It's like, he cannot sit idle. I know some people might say, well, what if he is sad and he is not doing anything? Well, we don't take that case into account. You have to be doing something. You have to you have to be in one of the observed states. Now, what else are you given? So you are given initial emission and you are given the transition probabilities like sad to sad. If at time one you are in a sad state, what is the probability that you will jump from sad to sad state? So that is 99%. This is the time one, this is time two. Similarly, if you say sad, then sad to happy transition is 1%. Happy to sad 10%, happy to happy 90%. So what you do is you flip a coin and you say, okay, what state do I land into? So that's the example. So just to recap, you are given three things in a hidden Markov model. The priors, which is prior of classes of hidden states. That is the first thing. The second thing you are given is emission probability. The third thing that you are given is transition probability. And this is the information that is needed for HML. So my claim is if you know all these things, you can figure out everything that you need to know about a hidden Markov model. That's my claim. And let's see if that claim is valid or not. Okay. Now let's look at a very simple example. Suppose the robot observes you at 3 times. First time you are watching the Game of Thrones, time 2 you are Facebooking, time 3 you are crying. So I have the observations, observable state, the hidden state, observable state. I know observation 1 is W, then something happens in the background and I observe the person Facebooking, something happens to the mood of a person and then the person starts crying. Now, this is the idea behind hidden Markov models. So we'll try to solve this. We'll try to guess what is the state here, what is the state here, what is the state here. We'll try to guess this answer. Now, you might say, okay, fine, we do that, but what is the application of hidden Markov model? Well, application could be many applications. For example, speech recognition. So maybe the person wants to say A, and that's what the person has in mind, and the way the sound that you get, that is the observable. So you might say, some people say A in a different way. Similarly, you have Z or Z. So when you have this thing, the American way to pronounce it is Z. The other way is to pronounce it is called Z. So you should be able to, say the person is, if it's saying Z or Z, he means the same thing. So that is speech recognition. NLP is, if you take NLP class, you will see that the first few chapters will be about HMM. Similarly, handwritten recognition is, there is the character A, but some people may write it as this, some people write it like this. Similarly, there is um, B, and some people might write B like this, some people might write B like this, and so on. So recognizing this and predicting the hidden state. And stock market, genomic sequence, etc., etc. All of them are key things to understand. Now, another thing is, so these are the, the things that I just pointed out, is recognizing each of these. Now, so in this case, I mean, just to let you know, this is might be the observations, and there might be some hidden state behind it. So that is how you represent the sequence data. You can work with such an example, and the principles that we learned in binary net or Bayes net still apply. So what did we say the probability or joint probability of n variables is according to first order Markov model? So the first order Markov model says P of x1, P of x2 given x1, because x2 depends on the previous person, which is the parent, is this. X3 depends on this. So I know the parents, I could multiply this out. So what have we assumed? We have assumed first order Markov model. So this is by first order Markov model. And you can write it as follows. You can say, okay, well, I'm sorry, I take that back. This is not first order. This is a general thing. This is the whole thing. Then mth order. Now, special case of Bayes is you take the first order. So this is most interesting. We are not going to worry about these because these are too complicated for us. Mth order goes back m steps. So this thing means current step depends on m ancestors, or m level of hierarchy, is that is what it represents. Now, we don't want to go there. We just want to go to state one, order one. So order one is most interesting, and we talked about this. We're going to talk about this. My assumption is x2 is determined completely by x1, x3 is determined completely by x2, and so on. So this is my first order Markov property that we're going to focus on. So generally, this is good enough. I mean, you could go to second order, but I'm gonna focus on the first order. So second order would mean x3 depends on x2 and x1. Okay, so we are just going to focus on this thing. This will be our main concern, and this is going to give you the parameters needed. And I'm not going to cover this in a lot of detail, but you can prove that if you have this sort of a scenario, which is first order Markov model, and you have a k-ary variable. What does that mean is x, the variable that we have, can take 0, 1, that will be mean binary, and if it can take 0, 1 up to k, I should make it better, so I should say 1, 2, all the way up to k. That will be called a k-array variable. So k equal to 2, it's called binary. In general, it is called k-array. You can prove that for this condition, it would be O of k square um, complexity. So if k equal to 2, if k equal to 2, what will be the complexity? It is O of 2 power 2. Just simply so on and so on. So as you go ahead to a higher level of Markov, the complexity goes up and up. And the proof of this is available here. So, and so you will have to figure this out. So I am suppose in n minus 1 state 1. I can jump to any of the states in um, time n. So I can go from 1 because xn could be 1 and I could go to any of the k states. So I need k minus 1 variables for 1. So how many variables would I need for all k? Will be k times k minus 1 or order of k square. Similarly, you can work through them and I'm not going to focus this too much. If you have m order dependence or if you have, sorry, m variables, so you could say this, you could make a table like this. I have um, xn minus 1 and xn. The first case, which is right here, from 1, I can jump to, okay, you go backwards. So you go backwards and you can figure that out. Mth order, which means you go back uh, n minus 2 all the way up to n minus m plus 1. You go back here and then you can figure out the case. Okay, so that is figuring out the complexity, that is figuring out um, the details, but theoretical details. But let's go to the practical understanding that we will be using most of the time. So we will be considering this as the Markov model, and our we are going to focus on implicitly it will be implied that we are going to focus on first order Markov. We are not going to go to second or mth order, first order. Now, what does that mean? What am I given? So I'm given the initial probability, also known as a prior. What does that mean? I know how likely is the person to start in one of those states. For example, state 1 could be pi 1. So I could have pi 1, pi 2, which is a vector, and the vector could be 20%, 80%, which says sad state, happy state. Then I'm going to be given the transition probability and emission probability. So I hope you understand this whole situation. Now, this is we went covered this earlier. Now you could be asked a simple question is what is the probability of this? I'm going to tell you what I mean, but you could be asked this probability. So the joint probability of something. So the way you will figure this out is this. Suppose you are given this thing. You will start off with some state, transition and output. So let me, rather than being very theoretical, this is what it means actually. So, this is what it means right here. Uh, let me break it down so that you don't get confused. Let me go back and give you the example right here, which we started with. Okay, this is the example that we were talking about. So the observables are WFC here. What is the probability that it would be SH, SHH? What is the joint probability of this? So the joint probability of these set of observables and hidden states will be this. What's the starting thing? Starting thing is what is the probability of starting in the sad state? Then in the sad state, which is sad state, which is time 0 or time 1, let's focus on this sad state, and then there is output, which is sad state, and I'm going to call that emission W given sad, and then I'm going to make a transition, which is P transition from happy given sad, and so on. So this is, I'm going to keep on doing. The best way to understand this is another example. Is this. Suppose a casino has two type of dice, and there is a casino player playing, and there are two hidden states. This is called hidden state. It has two hidden states, fair dice and loaded dice. Hidden state obviously implies that you are not observing the, or you cannot see what is the hidden state. That's obviously what it means. Um, so then there is an observable state. So let's see what are the parameters of this casino. And this is the parameter. Fair dice, if the dice is fair, because I have the hidden state 1, which is fair dice, the probability of each of the 1 to 6 numbers is same. So, I mean, it is not biased in any way. The H2, which is the loaded dice, has probability of 6 as 50% and the remaining as 10%. So obviously it is a biased coin. And I have one more piece of information is the casino switches back and forth between fair and loaded with 5% probability. So I can make a table for that, fair, loaded, fair, loaded. So this is time 1 or time xn minus 1, and this is time equal to xn, one step later. So fair to fair, the probability is 95% and 5% chance that he will switch state. Similarly, L to F, 5%, and this will be 95%. So this is what we mean by this statement right here. Okay. So I have whatever I was looking for. Now, suppose this is observable, this is hidden, this is my hypothesis of hidden. So how would you say, well, how likely is this whole thing? How likely is the joint probability of S, where S goes from 1, so this is 1, 2, 3, 4, 5, 6. S goes from 1, or I can write Sn, n going from 1 to 6, On, O going from 1 to 6. How likely is this scenario? Okay, we're going to figure that in a minute, but uh, let's recap, or let's see what the parameters are. So these are the parameters. Let's just summarize whatever we did earlier. Now, and this is just summarization of whatever we did earlier. Now, so let's tackle a question. So since we have these things which are given to you, the whole thing. Now, with this model of the HMM, suppose this is observable, this is hidden. And as I said, I want the joint probability of observable and hidden for time t, the whole thing. So where does the game start? The game starts in fair state. What's the probability of starting in the fair state? Well, you would say 5, 0.5, 50%. Then what happens is the game is in a fair state, and this is the starting t equal to 1 fair state, and then what does it output from the fair state? 1. So probability of outputting 1 given the fair state. Then what happens? There is a jump from fair to fair jump. So let's figure this out, probability of outputting 1 in the fair state. So let's see what does it mean. Probability of outputting 1 in the fair state is 1 over 6. So this is 1 over 6. Then jumping from fair to fair, what is the probability of that? Is 95%. Okay, then I go into fair state again. What do I output? Well, output 2. The probability of that is 1 over 6. And then I jump from F to L state. The probability of that will be 0.05. So I'm simply multiplying these values, and L state outputting what? Outputting 6. So probability of outputting 6 in the L state. You know that what is that? That is 50%. Then I make from loaded to another loaded jump, which is 95%. And then in the loaded I output 6. That will be 50%. So this is my likely observation of this and the states and the observable. So it's like, what is, you can ask, what is the joint probability of these observables and these states? So it is a joint probability. That is why I emphasize this, and this would be the answer. So whatever I have just done, it is summarized here. So you can be asked some questions like, hidden state, observable state, and you have a game. So game may be uh, fair, 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 loaded, loaded, fair, 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 loaded. And then you can say 1, 2, 6, 4, 3, 6, 6, 6, 4. Let's say one of these is 3, one of these is 2. Let's make this 6 and 2. So you could have this scenario, and I can ask you what is the probability of joint probability. So this is joint H, F, F, L, L, F, 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 L. This is one case, and the second case is 1, 2, 6, 2, 6, 2, 3, 4. And you can figure that out and give me the answer. Basic question, you can be asked this type of a question. So now this question is very easy. Um, it's almost a trivial question. What else do we do in hidden Markov model? I mean, if it was just this up to here, you would say, okay, it's a really easy case. Okay, so what is the next step? Well, what type of questions can you ask? Can you be asked in a hidden Markov model? Well, you could be asked a question is given a role by the casino players. Like this is the observable states. Oh, this. You can be asked how likely is this sequence given our model of how the casino works. So you can say, well, I don't need you to tell me the hidden state at each time. I don't really care for that. So how likely is O? That is one of the models. Like how likely am I to get this given my model of the casino? That's one of the questions. That is called evaluation problem. The second could be what portion of sequence was generated by the fair and what portion by the loaded dice. This means that is the question, maybe this is fair dice, this is loaded dice, this is fair dice, and then this is loaded dice. So I would like you to answer this question is which portion of the sequence was generated by the fair die and which portion by the loaded dice. That is called decoding question. So this is evaluation. This is called decoding. The third type that we might have is parameter estimation. So suppose you are given this observations. Now I tell you that there are two states that can be producing this fair state and loaded state. I do not know the parameters of fair or the loaded. I also do not know the transition or anything else. Now, given this model, now that's a difficult question, is given this model, you tell me the parameters of fair state, loaded state, the jump state, jump probability, and the initial probability. So it's like a chicken and egg problem because you are not given anything much, but you are given observables, and you have to figure out which was generated by which, and then you have to tell me the parameter of each. So this is called the learning question, which is obviously the hardest one, and maybe in advanced classes you will be working with this. So evaluation, which is the first thing, decoding and learning problem. Now, the thing that we do for evaluation is called forward algorithm. So forward algorithm is how you evaluate how likely is this sequence. So I'm going to give you a sequence. You tell me how likely it is. That is called evaluation problem, and generated, the way to solve it is forward algorithm. Okay. Then the decoding problem, which is step 2, could involve the following. What is the probability that the third roll was loaded given the observed sequence? Now there are two algorithms for that, forward, backward, and Viterbi. So it's like I'm giving you a set of observations. So I'm giving you O, hidden states. I am not really interested in all of them. I'm simply saying maybe 6, 4, 3. So I want you to tell me at time 3, what was it by loaded or was it by fair? That is called decoding question. The third one, which is kind of tough, we are not going to talk much about it. There is an algorithm called Baum-Welch algorithm based on EM that can solve this for you. It's a tough one because you're given not much information to work with and you have to solve that. So we are not going to worry too much about it. We are going to worry with the forward algorithm and the Viterbi algorithm. That is the thing that we are going to worry about. So evaluation and decoding problem. So how do you solve the evaluation problem? Well, the evaluation problem is figuring out the probability of observables. So I just tell you, here is the observable, find the probability of this. So what do you do? Well, you do this. You break it down into this. I told you, what do we do when we do not know something? Well, when we do not know something, we sum out all possible cases of that. So there are three possible states. I'm going to sum them out. So I'm going to say P of observables, which I know, and summations ST, and I do not know anything about the hidden state or the state. So I'm going to sum up over all possibilities. Remember, I had the question like, so there is a train strike here, 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 here. What's the probability of student A being late? And this is the train strike. So you sum out over train strike because you do not know whether train strike happened or not. So that is figuring this out is what you need to do. Somehow a complex problem. Can we break it down into simpler steps? Well, it turns out that we can. So we will define something called alpha. So alpha will be an interesting thing. Alpha underscore t and k. What does this mean? This means after time steps t, I am in state k. So interesting question. It says after time step t, we are in state k. For example, I could say alpha 4 hidden, which means after 4 steps, what is the probability of being in the hidden state? And so similarly, you could say what is alpha 5, um, sorry, this fair state. fair state, alpha 5 loaded state, alpha 5 hidden state, and so on. I could be given this type of a question. So I'm going to define something called alpha t state k. Now this is going to be very important and interesting for us because this will help us um, go forward. This will help us go forward with the idea. So let's look into this, and what we are doing is called the forward algorithm. So this is the idea of summation, and this is the idea of alpha something. So what is alpha 1 state pair? Well, you can easily figure that out because this means starting in the fair state and probability of outputting something, which is this, you know what it is, probability of outputting this given a fair state. That is what this means. And if you know alpha 1f, you could figure out alpha 2f and so on. So this is called the forward algorithm. So you start each step and you can go forward with the idea here. So for it to make more sense, we have to look at an example. Otherwise, it's going to be simply a bunch of theoretical ideas. So let's look at this thing. So alpha 1i, alpha 1 means after time 1 being in state I. So as I said, that is easy to fill out. So it's like probability of starting S1 in state I, then probability of outputting O1 given state 1 equal to I. That is 1. Now state 2 is going to be interesting because at time 2 being in state 2 can happen by two ways. Well, you can say state 1 at time 1, this is one scenario, or state 2 at time 1. And then you could go from here to or here to here. So you can say go from state 1 to state 2 or go from state 2 to state, so let's make this one, go from state 1 to 1, state 2 to 1. So S2, time 2 and so on. So let's look into the example of that. That is going to be more fun. So let us say I'm going to play a game, and in my game I have two states, S1 state, S2 state. Observables are R, W, B, and I am given the whole parameters of the HNM. Now I want you to tell me the observable. So there are two times t equal to 1 and t equal to 2. The state, hidden state, I do not know, but the observable I know as R and W. I know this. So now what would be alpha 1 1? Time 1 being in state 1. Can you tell me alpha 1 1 here and alpha 1 2 here? We need to figure these two out. So should be pretty simple. Alpha 1 1. Alpha 1 1 is starting in state 1. So starting in state 1, the probability of that is 80%. This one. Starting in state 1 and doing what? So pi in state 1, starting in state 1 and then outputting what? Outputting R in state 1. So what's the probability of state 1 outputting R? 30%. So I have this. This is alpha 1 time 1 being in step 1, state 1. Alpha 1 state 2. Well, alpha 1 2 is pretty easy to compute. Alpha time 1 state 2, which is probability of starting in state 2 and probability of outputting red in state 2. So probability of starting in S2 is obviously 20% and S2 outputting red is 40%. So alpha 1, so the way to do it, is to fill out a table. That's the easiest way to do it is since there are two time steps, make a table like this, and this is time one, and this is state one, this is state two. And I know that there is observable R, so I don't have to worry about it. So alpha 1 S1, alpha 1 S2. Then this is time 2, and I'm going to say alpha 1 S1, so sorry, alpha 2 time 2 S1, alpha time 2 S2. Okay, so the way the time 2, I'm going to observe W. Now, what is alpha time 2 state 1? Well, this could be two things. This could be alpha 1 1 multiplied by a jump from what? Jump from S1, I should write it. Jump from S1 to S1 plus alpha 1 S2 starting 1 S2. So it's going to be this jump or this jump. Alpha 1 S2 multiplied by probability of S2 S1. This plus there is also something is probability of S1 and outputting W. So this is what I mean, probability of outputting W in state 1, and that is going to be the sum of these two jumps. So because here I can jump from here or I can jump from here, this. So the bottom one, I can reach the bottom state by jumping from here or jumping from here. So that is this one. So I have computed alpha this, alpha this. Okay, so now I'm at step 2. The game ends at step 2. So what is the probability of R and W? So it is equal to alpha time 2 being in state S1 plus alpha time 2 being in state S2. Because time 2, at the end of time 2, you could either be in this state or this state, nothing else. So you sum these up and you get 0.1128 as the answer. Okay, so this is pretty straightforward. All you have to do is pay a little bit attention, but it's not very difficult. Now there is some practice questions here based on that I have posted, and let's go back here and look at some of the questions that are okay. This is kind of the same question that I had earlier. So you know that at time there are two times, time equal to 1, time equal to 2. At time 1, the observation was A, time 2 observation was B. Now I want you to first compute alpha 1 0. What does that mean? Is time 1 being in state 0. So how many states are there that we need to first figure out? There are two states, 0 and 1. So 1 and 0, time 1 being in state 0. What does that mean? Starting in 0, then probability of outputting A given state 0. Alpha, sorry, alpha time 1 state 1 is probability of starting in state 1, then probability of A given state S1. So can you look this up? Well, that's pretty simple. 0.3 multiplied by A in S0. A in S0. Okay. So this will be 0.9. This will be probability of starting in S1, which is 0.7, multiplied by probability state 1A. So state 1, because this is the state 1 and outputting A, that is 50%. So I have computed, and you can make a table like this. That's the easiest way. So you can make a table. This entry will be alpha 1 S0, or S0 can be written as 0, alpha 1 1. Now, how would you compute alpha 2 0 and alpha 2 1? Well, alpha 2 0 is probability of outputting B in state 0. So probability of outputting B in state S0 multiplied by two jumps. It could be either a jump from alpha 1 0 multiplied by probability of 0 to 0 jump, plus the second one alpha 1 1 probability of jump from 0 to 1, and this would be the answer of alpha 2 0. Similarly, you could output alpha 2 1 time 2 state 1. So alpha 2 1 you have computed, and alpha 2 0 you have computed. So what is the total probability of observing O1, which is, sorry, A and B? So probability of observing this is equal to alpha 2 0 plus alpha 2 1, because after two time steps you could either be in the 0 state or 1 state. So you sum that up and you get the answer. So the key part is to make a table, fill the entries of the table, and get your job done. So you might have to watch this one more time, and you might have to say, okay, can I really do everything that is given? There are some practice questions. You might want to go through them and practice the questions. So, okay, let's look at a couple of more things. Now, what have we done is we have figured out the probability of observables, which is OT, where T is going from 1 to final T. We have figured how to do that. If you want to be sure how to do that, is this is alpha capital T state 1 plus alpha capital T state 2, or state 2 plus whatever alpha T, and if there are K states, it is K. That is called probability of um, observing the states, or the observable. Okay, now the next question is even more fun, which is, it is a decoding problem. So decoding means um, I'm given a series of observations O1 up to OT. I would like to figure out what is the most likely state at S1 and ST. So what is the most likely state given the observation? So I earlier the task was to do this. Now the task is to do this. Now we are going to define something like previously, LVT and state. So VT state 1 all the way up to VT time state K. We're going to define something like this. And we're going to say, instead of this, we'll say take the max of this. So take the max, and it will tell you which state is it most likely to be in. So suppose in this case, V at time 2 t, Si is the highest. So I'm going to predict that at time t equal to uppercase T, the most likely state was Si. That is what I'm gonna figure out. Okay, so I hope this is somewhat clear to you. It's going to become more clear when we do the actual examples. So in Viterbi, what do you do is this. Suppose this is an example. In this example, um, there are two states or three states, S1 state, S2 state, S3 state. So this is the set of states. The set of observables are uh, A, C, T, and G. This is the set of observables. Now, you observe what? So you observed CCT. So you observed C, C, T. I want you to fill in the table and tell me at which value is the highest for each state. So this will be Viterbi time 1 and what is the state? S1. Viterbi time 1 state 2 and then Viterbi time 1 state 3 and so on. This will be Viterbi time 2 state 1, Viterbi 2 state 2, Viterbi 2 state 3. And then similarly this will be V3 S1, V3 S2 and V3 S3. Now the way you fill in this table is this. So what is the V1 S1? So that means starting in state S1 and outputting C. So starting in state S1. So starting probability is given to me as this S1, S2, S3. So starting in state S1 will be 1 over 4 and S1 and C. Is that even possible? So S1 and C is 0. So the first state is 0. Then I'm going to say S2 probability of starting in S2 is 50%. S2 and C, the probability of that is 50%. So it's 1 over 4. Then S3 starting in state 3 is 1 over 4. S3 and C is 1 over 4. So I do this. Now to figure out V2 time 2 state S1 is you have to do this V1 S1, V1 S2, V1 S3. You figure out this jump, or this jump. Whichever is the max of that, you have to figure that out. So V2 S1, you have to take the max of this thing V1 S1 multiplied by the probability of S1 to S1 jump. First term, so you have to take three terms V time 1 S2 probability of S2 S1 to S2 jump plus time 1 you could be in state 3 probability of S3 to from S1 S3 to S1 jump. The probability of S3 to from S1 jump S3 to S1 jump. So let's see which one of them is highest. So you know the V values. So it's 0 and S1 to S1 jump. S1 to S1 jump is this value. But since the first part is 0, you don't even have to worry about it. Then this jump, how likely it is. S2 to S1 jump. S2 to S1, 0.25. So this value will be 1 over 4 multiplied by 1 over 4. Okay, so this is okay. Wait, before I do that, this will be one more thing. This will be max. So V2 S1 is this, and it will be multiplied by something. It will be multiplied by state 2 time 2, which is time 2, and state S1. Now it turns out that S1 with C is not possible because S1 and C is 0. So because Viterbi time 2 S1 would be max of 3 terms multiplied by by probability of being uh, in state 1 at time 2. At time 2, you are in an observable C. So probability of observing C in time state S1. Probability of observing C in S1 is 0. So this term will be 0. The third term also, if you notice carefully, T and S1 is 0. So this whole window will be 0, or this whole row will be 0. Now let's look at Viterbi time 2 step 2. So this will be max of this or this jump multiplied by S2 state 2 and outputting C. State 2 outputting C is 50%. So that's why you have 50% at the start here. Now there is a jump from here to here, which is 0 obviously. Here to here, S2 to S2 jump. S2 to S2 jump, it is 1 over 4. So 1 over 4 multiplied by 1 over 4, that is the second thing. 0 into 1 over 2, that's the first one. Then what is the third jump here? S3 to S2 jump. S3 to S2, 0.5. So 1 over 16 multiplied by 0.5 is this. So now you have three values, which is the max out of 3. So first max out of 0. The first term is 0. The second term is 1 over 16. The third term is 1 over 32. So which is the max? Well, the second is the max. So 1 over 16, the second term, multiplied by 1 over 2. So this is you getting 1 over 32. Now you can figure out the same logic, how to figure out this term, how to figure out the probability the probability of time 3 being in the S3 state. So first thing, you take the max of three terms, which is like before, then probability of S3 given what? So given C. Okay. So probability, because S3 and C. So S3 and C, that is 1 over 4. So max of three terms multiplied by 1 over 4. That is what we have, 1 over 4 max of three terms. So what are the three terms? It is this. Look at this jump. This jump. So max of three terms. The first term is 0 multiplied by something. 1 to S3 jump. S1 to S3 jump is 0.25 or 1 over 4. And the second probability is S2 to S3 jump. S2 to S3 jump is 0.5 and 1 over 4 into 1 over 2. Why 1 over 4? This value. The third one is this jump. So S3 to S3 jump is actually 0. So 1 over 16 multiplied by 0. So this is obviously 0, 0. It will be 1 over 8. 1 over 8 multiplied by, what was that? Probability of outputting C in S3 state. S3 and C. So S3 and C is 1 over 4. So this will be 1 over 4, which is 1 over 32 here. Similarly, you keep filling the entries of the table. So when you are done, you look at the last one. So you look at the last one and you say which one is the largest. So I'm going to say this is the largest. Now you will say, let us trace back the steps from here. So how did I get here? So this is 0, this is 0. Obviously, I got here by this jump. Okay. So then 1 over 32, how did I get here? So this is, forget about it. This is low. I got here from this point. So now the most likely hidden state is S2, S2, S3. And that is the answer right here. So there can be various numerical examples based on this. I will solve a couple of them and I will leave that to you to solve more. Okay. Now let's look at the practice questions, and we'll look at the Viterbi algorithm based questions. Okay, this is a good question for Viterbi. So you are given the normal parameters of MM, and the states, the hidden states are two, healthy and fever. Now, so we're gonna make a table, healthy, fever, and we're gonna say how many days is the observation. The observation is for 3 days. The first day, the person was feeling normal. Second day, cold, and third day, dizzy. And I want you to trace back the steps to see which one is largest. So what will be the entry here? The entry here would be starting in the H state. Starting in the H state is 0.6. So this entry right here will be 0.6, then healthy normal. Emission probability healthy normal is 0.5. So 0.6 multiplied by 0.5, which is going to be 0.30. Is that right? Or 0.03? It is 30 and then 2 by 0.30. So the value here is 0.30. Then what is the value of next cell or the cell here? That is probability of starting in the feverish state, 0.4. Feverish state feeling normal. Feverish state feeling normal, 10%. So 10%, which is 0.04. So this is 0.04. Then what do you do? Well, you compute time 2 and here this value. And you take this jump and take the max of that. So healthy and C, healthy and C is 40%. So you're going to take the max of two things. And then you're going to multiply that by 0.4. What are the two max things? So 0.30, which is the top one, H to H jump. H to H is 0.7 into 0.7. And then the second thing is 0.04 multiplied by F to H jump. F to H is 0.4. So if you expand this, and you see which one is larger. So you will see this becomes 21 and 0.21, and this becomes 16. So the top one is larger. So I'm going to say how did I get here was this arrow. Then you can say how did I get here, and you can figure out the value here. Then you can figure out the value here, and then you can figure out the value here. Then whatever is the highest one, you use that to trace your steps back. That will be the most likely state of values. And we can work through that, and I mean it's very easy to get the answer. Similarly, there is one more question on Viterbi. Okay, this is the Viterbi again. Um, let's look at a good question for Viterbi. Okay, this is a good question for Viterbi. It's actually a bioinformatics data. So I have this observable right here. I have two state, H state, L state, two states. And I observe this. Let's suppose I go up to A. So I'm gonna make a table, and the table will have G, G, C, A, four things, and there are two states, hidden state and loaded state, H and L. I don't know what they mean, but H and L state. So what would be this value? This value will mean starting in the H state and then outputting G in the H state. So starting in the healthy state, are you given that? Well, you are given 50-50 starting state, hidden state. So 1 over 2 multiplied by healthy H state and G. H state and G 0.3. You can say this multiplied by 0.3. Now what is this one here? This one will be 0.5 multiplied by probability of G in L state. So G in L state is much lower, 0.2. So multiplied by zero point 0.2. So this will be 15, and this will be 10, and this. So this will be 0.15 and 0.10. Now that is fine, and let's look at what will be this value. So this value will be max of 0.15 multiplied by H to H jump, and H to H jump, which is here, is 50%. So 0.15 multiplied by 50%. Second case is 0.10 multiplied by L to H jump. L to H jump, which is this one, is 0.40. Then I have another thing, probability of G in H state. So probability of H state and G is 0.3. 0.3. So if you fill this value in, I'm going to say this, the top one will be 75. This one will be this. The bottom one will be with this. So take the max of this and then work forward. I think my system is saying I went too long. So let me quit this and then come back and see some more. So let me